So in today's episode, we are joined by Iman Dadras and Fatemeh Rastgar. How has Estonia been so far for you guys?
I can start. Estonia is, I would say, very nice country with nice people. I mean, they give you the privacy that you need all the time, and I kind of adore it and enjoy it at the same time. And also, I enjoyed the less amount of bureaucracy that we have here. I didn't have to go to any offices. I went to offices only twice in Estonia for bureaucratic paperwork, and that is really nice. Yeah. So I really enjoyed the Estonia, especially summer that we are now, very warm days. And, yeah. What about you?
So for me, it's also the same. I like that you don't need to go to offices to just do paperwork, and it is really good. When you understand it, then you go to another country. Then for a simple work, you need to put several days to just do a simple work. But yeah, I like the nature as well, and I enjoy it.
You as scientists, what could you say? How scalable is the Estonian e-government system in terms of bigger countries?
It is possible, but for that different organizations need to work together. Because I heard that some governments do not like to, some different organizations do not like to share their information with each other. And if they don't do that, this is not going to work well. But I guess different organizations doing this in Estonia very well, and this is the reason that you can do everything electronically.
I mean, theoretically, if you want to launch an e-government system, it is even more beneficial if you are covering more people, because the cost does not increase linearly with the population. But if you want to open physical offices, then you need to increase the number of offices and employees for each, linearly with the population. But the problem, I think, is more cultural and in the infrastructure. I mean, we don't have infrastructure in Iran, for example, but even in Germany, that has the money and everything to build government there, they have the problem of trust, because people does not trust the politicians like Estonia. I mean, they don't want to give all of the data and power to the government, as I understood. But here we have both infrastructure and your culture. I think is very positive about this as well.
We all know that scientists are busy people, but what are your hobbies?
Yes. Hobbies, I go to the gym like 3-4 times a day, if you can call it a hobby. And it is a hobby kind of, because after working hours on a study and job, it is really refreshing. But usually I go to the nature, to the Estonian forest here. If it is like an afternoon, I go to El Mazzalo. It's half an hour far from Tartu, but it has very nice forest and for a barbecue or something like this. If I have more time, like one day I go to Pangudi Lake for camping, and I especially like the view in the sunset or sunrise. If we stay there overnight over the lake, it is very beautiful. And sometimes we enjoy the mobility opportunity that we have in Europe, because we can go any countries, and if we have like 1 week, we go to visit another country as well.
What are your opinions on the Rail Baltica project?
It's even better because now when you need to go to another country, then you need to go to the airport, and it takes time. But if there are other ways, it's absolutely better. and faster. Yeah.
But the Rail Baltica doesn't come
But
directly to Tartu. I think it goes from Pärnu to Tallinn, so we still need to travel to another city. Because, I mean, we talked about the positive side of living in Tartu. I think the most negative aspect is that it's a bit far from, I mean, it's a bit hard to get to another places from Tartu. Because it's a small city and it is completely understandable. But Rail Baltica is very nice to connect Estonia to the Central Europe, especially for environment, because rail travel is way better for environment.
I'm just bluntly going to ask about your freshly defended PhD thesis. Congratulations to both of you. Iman, can you explain the potential applications of insect-scale robots and how they could revolutionize fields like environmental monitoring, search and rescue, and space exploration?
The main advantage that insect-scale robots have over the conventional robots are their form factor, their size. They are very small. And so we need very few material to build them. So we can produce many of them cheaply after the R&D phase, because during the R&D the price would be high because of all of the money and cost of the research and development. So it is very important for the applications that require operation over vast area. For example, after a natural disaster, we can deploy a swarm of insect-scale robots to the impact area. And because they are small, they can go into the ruins and look for the survivors, and after that they can inform the search and rescue team of the survivors' location, for example. But for example, for space exploration, the cost of sending an object to space is relative to its weight. So if we have insect-scale robots that are lightweight, it is cheaper to send them to space. Also, we can send many of them, for example, to Mars, and to cover the whole Mars for taking like samples. And after that, we can even don't bother to take them back to Earth, because they are cheap and the material that actually we put there is not that much. So these are like the potential applications that they have, but they can have many more applications as well.
What would be the interests of big industrial companies in these regards?
In a petroleum plant, for example, we have a lot of pipes, and you may have some leakage, and we don't know on which pipe is it. But if you have insect-scale robots, they can go between the pipes, and with the sensors that we mount on them, they can find the leakage, and then it reduces the maintenance cost a lot, for example, as one more industrial example.
Interesting, but Fatemeh, can you describe the innovative trajectory optimization algorithms that you developed and how they improve reliability, scalability, and computational efficiency?
The optimization algorithm that I'm working on that aims to find a trajectory for a robot between the initial and final points, while it's satisfying some constraints like avoiding obstacles or robot itself dynamic and kinematic constraints. So what we are doing that first we get the position of the obstacles, and then we know about the dynamics of the robots, and then we have the optimization part, which somehow optimize the trajectory based on the constraints that we have, and then find the path.
What would you say are main application fields for trajectory optimization?
Trajectory optimization is a fundamental component of almost all robotics applications. So for the ones that I'm working, it can be applied on autonomous drivings, or a robot which transfers blood samples or medicines in hospitals, or healthcare facilities from one point to another point, while it doesn't avoid with people, walls, and it also can find its path.
How did you test trajectory optimization?
So I tested in this room. So I made some obstacles and barriers which are constant, also they are moving, and then I put a robot and asked the robot to move from one point to another point, and the algorithm was able to navigate the robot in a way that it can go find the trajectory and also satisfy all the constraints and doesn't avoid with any obstacle.
So Iman, what are the primary challenges in achieving power and control autonomy in insect-scale robots, and how does your research address these issues?
The main challenge is miniaturization itself, because when you make things smaller, it is harder to accommodate everything on board. And autonomy very simply means that you have what you needed on board. So you need to have the electronic chips on board, and as well the battery, and we'll have a very tiny actuator that can be able to carry all of this. And that is when the problem comes, especially if you want to do complicated tasks on board. Then you need bigger hardware, and bigger hardware is bulkier, and we cannot actually put it on the robot. And also this hardware requires power, and it means a bulkier and bigger battery at the same time. So the weight of these go beyond the payload limit of the robot.
To specifically address the power issue, what would be the best power storing solutions?
Supercapacitors are promising, but they are still in the R&D phase as much as I know about them. There are some combustion insect-scale robots that use actually ethanol or gas for moving, but the problem with those is that you provided the movement by combustion, like a car, a regular car. But what do you want to do for the electricity that you still need for the electronic chips? So I don't think that it is a very good idea to have like a dual powering system. So usually it is lithium-ion batteries these days still, but they are working at power harvesting scheme that they can get their energy from the environment. But this energy is too little for insect-scale robots still.
So does it have to do with the second law of thermodynamics?
Yes, kinda. For example, they mounted a solar cell on top of one of these actuators, one of very advanced ones that is developed at Harvard University. But the problem is that if they want to power the insect-scale robot with the solar cell, they need to put a powerful laser beam on it. It cannot work with the sunlight. It's not enough for it. So we need to power it more, and then it's not autonomous anymore because it cannot go out of the area that your laser is covering.
Fatemeh, how do your algorithms remodel kinematic constraints and collision avoidance constraints to enhance performance?
So the problem with optimization algorithm is that they have a feature called non-convexity, which means that convex means that the function that you have has a bowl shape, and because of this bowl shape, you're always gonna have one minimum at the end, which is the bottom of this bowl. But non-convexity means that there are several bowl shapes next to each other, and then you don't know which bottom of bowl you need to choose. So the way that I'm working is that I try to reformulate the optimization problem in a way that they have this convex structure, which means that they have just one local minima, and then I can get the result. Yeah. So this is the, it's more mathematically how I change the problem, and then I reformulate that in a way that I can find the good results for that. So the LiDAR gives some point clouds to us. Then I change these point clouds to the positions of the obstacles that I have, and then I predict the next position of that obstacles. So what I have here in my algorithms are positions of the obstacles. So then I need to write the algorithm in a way that the trajectory that I'm generating doesn't collide with these positions. So the changes are inside how I write the obstacle avoidance conditions and reformulate that. It's not directly related to LiDAR itself, but also it's related to the positions that I get.
What are the main issues with trajectory optimization?
Trajectory optimization problems have two main issues. One of them is the scalability issue, which means that if I increase the number of points or obstacles that I'm seeing, then it's hard for robot to manage all of them and then produce a feasible trajectory. So and the other one is that for each trajectory optimization problem, we need to have some initial guesses about the possible trajectory that we can get, and this initial guess can change everything in our problem. So what I'm doing is that somehow I'm managing how to make the algorithms more scalable in the way that they can get more obstacles and they can handle them better. And the other one is that how I can manage this initial issue and give the better initial guess to the problem itself.
Is scalability a big thing with trajectory optimization?
Let's say that I have 10 obstacles and robot easily can find its path. But if this 10 goes to 1,000, then it's hard for the robot to find a feasible path. For example, for the LiDAR itself, the ones that we are using gives about 700 points at each time that it updates the environment. So consider that we need to consider 700 points as obstacles positions. It makes the algorithms too hard to just find a feasible trajectory. If I use just the usual, the existing methods, the state of the art, they somehow can reduce the problem to solving a problem which has a big matrix. And when I increase the number of obstacles, number of points that I can see from the environment, these matrices become bigger and bigger. And then computing this big thing is too difficult. So what I'm doing is that I show that the size of this big matrix doesn't correspond to the number of obstacles that I have. It has a fixed shape, and it doesn't matter how many obstacles I have. It all the time can be computed easily.
Iman, to go further on, how do piezoelectric actuators function in flying miniature robots, and what are the limitations related to power and payload capacity?
Piezoelectric actuators are known for decades now, and they are used in many things, even in the many speakers that you have. And so very simply, if you apply the electric voltage, they change form. They become bigger or smaller. And they use this ability to move the wings and make the robot, for example, to fly. But the problem is that they require high voltages, for example, 50 volt, and you have usually less than 5 volts on the battery. So if we want to use these piezoelectric actuators, we need to have DC-DC converters. And DC-DC converters are bulky. They are like power electronic circuits. And so this DC-DC converter itself takes up a significant amount of the very limited payload that we have on the insect scale robot. And also, the efficiency of DC-DC converter is not 100%, so we are wasting a part of the limited power that I have, the limited energy that we have on board on the DC-DC converter.
Is this due to a thermal loss?
Yes, yes, it is thermal loss.
And they have been around for, you mentioned, maybe decades?
Decades, I think. Maybe even they are known for longer time, for a couple of centuries, but they are in vast utilization during the last decades, at least, I would say 60, 70 years.
And have you researched any alternatives to this to solve the payload problem?
Actually, yes, we have ionic electroactive polymer actuators, or IAP actuators. It is developed at, I mean, not originally developed, but they kind of built on this field a lot at Tartu University. So, yes.
Conducting polymers.
Yes, yes, exactly. And there were like a possibility for me to do experiments on them, and I found them a good alternative for Tressia, for crawling robots that move on the ground, not the flying one, because the bandwidth is low for these actuators, so they are not a good choice for flying robots. But for the terrestrial robots, they are a good alternative. Mostly because they can operate at low voltages. You don't need a DC-DC converter for that, for them.
Is it, you mean like an inverter, or what the opposite of an inverter? Or like going from high voltage to small voltage?
Kinda, yes. It is, a DC-DC converter is a bit different, because inverter, the input of an inverter, if I'm not mistaken, is AC, and the output is DC. But here, both sides will have DC voltage.
A question to both of you. What is the significance of your scientific endeavor?
The significance of it. I mean, I am an electronic engineer, so I did some work on the actuator also, and that is, I would say, also important, but I like my work on the electronics better. And the part that I think it's very important, I want to continue developing upon, is the hardware network co-design in artificial intelligence. Because usually people are expert in one of these fields. They only work on the AI network, machine learning network, or they are working only on the electronic hardware. But the work that I've done is like I look at it as one picture, and I try to optimize everything, and my output was only the accuracy. So from the bare metal, kind of transistor level, up to the CNN network, I look as one system, and I try to optimize everything there to work with each other perfectly in order to increase the network level accuracy at the end of this loop. So it's like that I have the exact amount of precision in my For example, transistor level design that is needed to achieve a high accuracy at the network end. And I think it is very important if we want to have edge processing, because now we have very good models, but all of them are working on cloud computing. All of them are done on the cloud side. So, but if we can have processor and enhance their efficiency and performance, then we can have also edge processing, and edge processing unlocks many applications, and this insect scale robot is only one of them.
The magic word is AI and machine learning in my field and almost all the fields. So I think that the combination of learning methods with optimization can boost the performance of the algorithms very well and open new doors for us.
How does AI help you in your everyday work?
Writing,
Writing maybe.
searching.
Writing more. Yeah, you can get ideas from the, I want to make this slide. How is better? Then you get some ideas and you can think about them.
But we need to be careful because
Sometimes,
not all of the data is correct, and sometimes it is like very
Wrong.
I don't want to say biased, but I can't find a better word for it. It is like doing only things one way, but maybe sometimes you want to have another effect on your audience. So we want to do it another way, but it is like knows only one way that thinks it is the best one.
When will we reach artificial general intelligence or a point of singularity?
I don't know, but if it is not happened already, it is happening
Soon.
Near future, I say.
Well, it's been awesome, and thank you guys so much for participating in the podcast.